This is section 2.5. In this section, we're going to be discussing transformations of graphs. Okay, before we get into any transformations or any examples, let's just kind of build a little library of known functions. And remembering what the graphs of these functions look like will help you in pre-calc, in Calc 1, Calc 2. So it's not a bad little idea to kind of keep these little functions and their graphs just sort of memorized. Just makes your life a little bit easier later on. Once you recognize a similar graph, you'll be thinking what the parent function is. So we're going to call these things the parent functions. We're going to build our transformations based on these parent functions. Okay, so we have the identity function y equals x. And actually, as a matter of fact, just any linear function, anything of the form y equals mx plus b, you should just be able to recognize it as a line. That's kind of a useful thing. If our next function here, y equals x squared. So this is called a parabola. So we have a little parabola. It's the simplest form of a parabola that we could have. We could get it more complicated, but right now this is our parent function. Y equals x squared. We have a parabola. The square root function, if you notice the square root function, it starts at 0 and goes towards positive infinity. And actually what we should be doing here also is stating the domain and the range for all of these things. So let's see. So the domain for this one is definitely negative infinity to positive infinity. The range also negative infinity to positive infinity. Over here in the case of y equals x squared, the domain. So how far to the left, how far to the right does it go? Well, it goes from negative infinity to positive infinity. Now the range, how far down, how far up? So from how far down to how far up does it go? This guy goes from 0 to positive infinity. For the square root function, the domain is from 0. It's from 0 to positive infinity. And the range is also the same, because this function goes from 0 and keeps on going up forever. We have what's called the cubic function, x to the third. This little curve here, its domain is everything, negative infinity, positive infinity. Its range also, it's negative infinity to positive infinity. Cube root, the cube root function, notice that the cube root does keep on going into the x-axis. The cube root and the square root are sort of related. It's just that an even root, a square root, the input for a square root cannot be negative. That's why my graph cuts off right here at 0. But for the cube root function, it's okay if the input is negative, because for instance I could have the cubic root of negative 8, and turns out that that is not a complex number, that's just negative 2. Because whenever you ask yourself what's the cube root of negative 8, what you're asking is, can I find a number that whenever multiplied by itself 3 times gives me negative 8? And well, that's negative 2. So the cube root function, we see its graph here. Its graph also is kind of similar to the graph of x cubed. Turns out that there is a relation between the graph of x to the third and the graph of cubic root of x. Turns out that they're inverses of each other, and we'll talk about that later down this in another section further down the line. Here the domain of the cubic root function is, well, negative infinity to positive infinity. The range also is from negative infinity to positive infinity. We have the function 1 over x. This function here has a vertical asymptote at x equals 0. X equals 0 is the y-axis. And so there is no y value. There is no y value that corresponds to when x is equal to 0. So the domain then is from negative infinity to 0, not including 0, and then from 0 to positive infinity with a union in between. So the domain here is negative infinity to 0, union 0 to positive infinity. The range is similar. The range is, if you notice, from how far down to how far up does it go? Well, my graph keeps on going down forever, but my graph never crosses the x-axis. The x-axis is a horizontal asymptote of my graph. So my graph never crosses the x-axis, so then that means that the range is going to be from negative infinity to 0, also union 0 to positive infinity. Our absolute value function, that's also a good function to keep in mind. The domain is from negative infinity to positive infinity, and the absolute value makes anything negative positive. So then well, 0 stays 0, and that means that its range is going to be just from 0 to positive infinity. Okay, and there are other functions later down the semester that, or later down in your mathematical career, that you might want to just sort of memorize, like sine and cosine, but once you get to pre-calc, you'll deal with that. But for now, these functions and their graphs are definitely worth your time to just keep in your mind. We're going to use them. Okay, let's start talking about transformations then. Let's begin with vertical transformations. So vertical transformations, that means vertical shifts, vertical stretches. Let's talk about that first. Okay, so imagine I was given some function f of x, and then to that function I just add b. Yeah, well, that just means that it's the function f of x, and the graph just got shifted up b units. If b happens to be negative, then we are actually just moving the graph down b units. Yeah. So here, I don't know. So let's see. If b happens to be positive, so they told us if b happens to be positive, then the graph of f of x plus b is the graph of f of x shifted up b units. Here there's a little mistake. Let's change this mistake. This should be a negative right there. So the graph of f of x minus b, that's when we are shifting the graph down b units. Sorry about this mistake in the notes, but change that to a minus there. That's what was supposed to be there. Okay, so then let's think about this. So let's graph some little things here. So if you think about it, this x squared, so this first little graph here is just the parent function. Let me say here, parent function. So the parent function for this one is what function? So I would say that the parent function is y equals x squared. That's the parent function. Yeah. So I know what that looks like. It's one of our parent functions up here. It's this guy, and what the plus 6 did, what this plus 6 does is just moves it up 6 units. So let's see, 1, 2, 3, 4, 5, 6. So that's right there, and I have my parabola again. It's definitely worth your time to know what the parent function is. So here the parent function was x squared. What the plus 6 did is just move it up 6 units. Yeah? Okay, good. Let's see here. The parent function here, the parent function is y equals cubic root of x. Yeah? And let me remind myself what it looks like. The cubic root of x, okay. So it's this little sideways little curve. And what I'm doing to that sideways little curve, what this minus 6 does to it is it brings it down 6 units. Yeah. So let's see. Originally it crossed the x-axis, that's where it had this little curve. Now that happens 6 units down. So let me count. 1, 2, 3, no, 1, 2, 3, 4, 5, 6. Alright, so kind of right there, that you can think of this point now as being sort of like the origin originally. My graph does something like that. Yeah, so it was just the original function x cubed, the parent function x cubed, but then all of this just went down 6 units, 6 units in our case. Alright, so these are called vertical translations. So this is a vertical translation here, or a vertical shift. Let's call these guys vertical shifts. Okay, so we're shifting the graph. The graph doesn't change shape. All it does is you shift it. You slide it to the up or down. Let's talk about horizontal shifts. So here we have some horizontal shifts. Okay, so let's see. So if you are given some function f of x, you start with f of x originally, and then if you have f of x minus d, if it's minus, you're going to be moving d units to the right. If it's plus d, you're going to be moving d units left. So here's a little bit counterintuitive. If it's plus, you're going to be moving left. If it's minus, you're going to be moving right. So let's graph some things here. These are supposed to be shifts. Shifts. Alright, so here, what's the parent function here? I would say that the parent function is just y equals x squared. So y equals x squared. That's my parent function. Yeah, this is what I started with. That's my parabola. What does the plus 6 do to that parabola? If it's plus, we said it goes to the left. So now I have to count 1, 2, 3, 4, 5, 6. That's right there. That's the origin of my new parabola, and I have my parabola doing whatever my parabola does. Yeah. So again, you always gotta kind of think about the parent function, and then it helps. Okay. Let's think about the next example here. So here my parent function. The parent function is the absolute value of x. Okay, and we know that that's just a little v, and it has this little pointy point, I guess, at the origin. That point is called the cusp. And what is this plus 4? What did this plus 4 do to my graph? Well, the plus 4, what it does is it moves it to the left 4 units. So to the left 4 units, 1, 2, 3, 4. And then I have 1, 2, 3, 4. Alright. Okay, so these are called horizontal shifts. Horizontal shifts are a little bit counterintuitive. If it's plus, it's to the left. If it's minus, it's to the right. Okay. Next type of transformation, reflections. So let's see, let's think about reflections. We have two types of reflections. We can reflect with respect to the x-axis and the y-axis. So the graph of, if you put a negative in front of your fraction, if you put a negative in front of your function, then we are reflecting across the x-axis. Now, if it's your negatives that change sign, then we are reflecting with respect to the y-axis. So be careful with that. Yeah. So if the negative is outside your function, you are being reflected with respect to the x-axis. If the negative is inside the function, we are reflecting across the y-axis. This is kind of like the even and odd sort of situation that we had before. Okay, Let's see. Let's just kind of get into an exercise. I'll let you read this next little sentence on your own. So let's see. So here I'm thinking, okay, I want to get a sketch of the graph of this. So first of all, I gotta identify my parent function. Parent function is y equals cubic root of x. Okay, so the cubic root of x, I know what it looks like. I can refer to the graphs up here because we have the list of parent functions. So cubic root of x is this guy right here. Alright, and so now that graph, let's keep it in mind, has been reflected. I'll sketch it down here next to what we're doing. So let me just make a little sketch here just for reference. That's an ugly little sketch, but you get the idea. So now this negative right here, if the negative is outside of my function, which it is right now, it's negative my function, I am reflecting across the x-axis. So think about this little graph and imagine that everything gets reflected across the x-axis. So this bottom part, this part that was underneath the x-axis now is above. The part that was above the x-axis now is underneath. Okay, so then I think what it ends up happening is that my graph kind of does this. That's an ugly little sketch. I apologize, but you get the idea. I mean, this is the parent the function over here on my left, and you know I had this little part that was underneath the x-axis, and I had a little part that's above the x-axis. Well, they changed now because they got reflected on the x-axis. Now let's think about this guy. So this function right here, the cubic root of negative x. Notice that the negative is now inside of my function. Well, that corresponds to a reflection on the y-axis. That corresponds to a reflection on the y-axis. Okay, so let me look at my parent function. My parent function originally kind of did whatever, you know, from bottom left to upper right. Now you gotta think about reflecting that on the y-axis. And well, the reflection on the y-axis is going to kind of actually look identical to the reflection on the x-axis. Why do you suppose that is? Why is it that the reflection on the x-axis for this function is equal to the reflection on the y-axis? Well, that's because this function is odd. Yeah. This function happens to be odd. Okay, so keep reflections on the x-axis and the y-axis. Be able to tell the difference on where the negative is placed. Let's think about now the next transformation. Let's talk about vertical stretching and compression and stretching, or shrinking, whatever you want to call it. Vertical stretch and shrink. So right now we are kind of stretching the graph vertically or compressing it vertically. So if we are given a number a that multiplies our function, yeah, so imagine that it was like a number times a function, then depending if a happens to be bigger than 1, so if this value a happens to be, so if the absolute value of a happens to be bigger than 1, then we're stretching the graph vertically. If the absolute value of a happens to be something less than 1, like 0.2 or something like that, then we are shrinking vertically. We are multiplying the y value by a. Okay, so then for instance in this case, here, this 3, this is a vertical stretch. This is a vertical stretch. And if we needed to be careful, so for instance here the parent function also, parent function is y equals absolute value of x. And I'm going to sketch the parent function down here just for reference. And I'm actually going to label a couple of points. I'm going to label this point 1 and 1. So that's what my parent function sort of looks like. And the point 1, 1 is definitely on my parent function. Yeah. Now let's consider this new function, 3 times the absolute value of x. So 3 times the absolute value of x. Okay, well, this is a vertical stretch, we said, because 3 is bigger than 1. And look, let's look at the original point that we had in the parent function. We had this point 1, 1. Yeah, so now if my x is 1 over here in my transformation, then my y is now 3. So now I have the point 1, 3. So my graph kind of got a little bit skinnier and sort of steeper looking, yeah? The parent function is a little bit more open, more wide. Now this thing is a vertical stretch, yeah? It's a vertical stretch by 3 units. Now the 1/3 right here, this is going to correspond to a vertical shrink. So now I have the point here 1, and or rather that has coordinates 1, 3. Sorry, 1, 3. Now let me look at this vertical shrink here. So originally my graph, the parent function went through the point 1, 1. So 1, 1. That was a point on the original parent function. This 3 right here made that point go to 1, 3. So that's a vertical stretch. And now what is going to happen over here with this vertical shrink is that I'm going to have 1, 1/3. So now I have the point 1, 1/3, which is right there, and now my graph is way kind of wider looking. And they're supposed to be symmetric with respect to the y-axis. I'm sorry, it's kind of... So this point right here should now have coordinates 1, 1/3. Yeah, this point originally over here was 1, 1. So vertical shrink by 1/3. Okay, let's see. Let's talk about horizontal stretching and shrinking. Horizontal stretching and shrinking is a little tricky, so be careful with this one. Let's see. So now if you have a number that's inside of your function, yeah, if that number happens to be less than 1, so if it happens to be less than 1, the second part down here, then you're actually stretching. If it's bigger than 1, and the reason why we talk about the absolute value is because let's ignore the sign for a second. I don't care if it's negative. I mean, if it happens to be negative, then I'm dealing with a reflection on the y-axis as well. But if I ignore its sign and I just look at the number, if the number is less than 1, then I'm stretching the graph horizontally. If the number is bigger than 1, then I'm shrinking the graph horizontally. So let's see. Let's answer a few of these questions here. This is a tricky. This horizontal stretch and shrink is tricky. So definitely try to wrap your head around this early on. So imagine I have a function, r of x, which is f of 2 of x. So here what ends up happening, so in this particular example, the parent function, my starting function, is f of x. I have no idea what it is, it doesn't matter. What they said to me is, so originally you had some function f of x, and now we've created a new one called r of x. R of x is made up of the original one, the parent, except that you multiply by a 2. What does that 2 do to my original function? Turns out that since this value 2 is bigger than 1, so this value is bigger than 1, we are shrinking horizontally. This is a shrink. This is a horizontal shrink. Why? Because 2, the absolute value of 2 is definitely bigger than 1. Yeah? Now, let me think about this other function. Actually, in both cases here. So the parent function is f of x, and then we created a new one by multiplying the inside by 1/4. Now, since the 1/4 is less than 1, we're dealing with a stretch, horizontal stretch. Yeah, so be careful with this. It's kind of a little bit maybe counterintuitive. If the value is less than 1, you are stretching. If the value is bigger than 1, you are compressing, you're shrinking. So let's think about some, well, actually now, in the next part of this video, we're going to go through these examples. So we're gonna kind of follow all of these examples. So let's, right now, this was the first part. We'll do the examples in the next part. Thank you. So stay tuned, and I'll see you in the next part of this video.